when we write out a probability model, that can only get us so far, right? And writing out the sample space, we can do some things with it, but then more general principles are going to be hard to determine just based on that alone. So what we need to do is talk about a way to disperse the probabilities, right? We know that by rule one, right, all the probabilities must be between 0 and 1 for all the different outcomes, inclusive, I should say, 0 and 1 inclusive, and then the probabilities must all sum to 1, right? We know those, and so what we need to do is take the probabilities and distribute it according to the different outcomes in some way. And so that idea is exactly what a probability distribution is. It assigns probabilities to the outcomes in some fashion. Okay, and so and that's actually all the definition of a probability model is it's a way um, to assign probabilities to outcomes. Okay. Now, when we have these probabilities that we're working with, right, they're going to occur in a variety of ways. Well, not variety, two ways specifically, and then those could have each appear in different fashions. They could appear in either discrete manners or continuous manners. Okay. And so we've talked about discrete and continuous variables, and that's very much in line with what we would see in these cases. So graphically, if you can remember what discrete and continuous visualizations for discrete and continuous data look like, we would see for the discrete case something like a histogram popping up. So we would have something like this, 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 and this, right? And then we would have, outcome 1, 2, 3, 4, whatever it is, and then we would have the probability along the vertical axis, okay? Um, and then for the continuous case, this one is a little tricky. We know, like, an example of a continuous graph would be a line graph. So we would have, something like this, right? And we would have, here's the one boundary of our interval. Here's the other boundary, and then we have a value somehow for every event in between there. And the only thing we don't really know is what that vertical axis is. And it actually is a little fictitious, I'll say for now. The method on this is the vertical axis is not going to be probability because we measure probabilities in a different way for a continuous probability distribution. So nevertheless, let's dive into each one of these probability models and see what they look like. Okay. So I went back into the demographic survey that I gave you at the beginning of the semester and found out that at least at the beginning of this semester, 51% of students in statistics said that they had dated one distinct person in the last 30 days, and then 2% had dated two or more distinct people in the last 30 days. And so what we want to do is create a probability distribution for x. Okay, so what we're going to use is x, and then with this we need to talk about a probability. Again, all a probability model is, it's a listing of all the outcomes in the sample space and then a probability with each outcome. Okay, so I have information about one person, and that was 51. I'm just going to put it as a decimal. And then I had information for two or more, and that was, what was that, 2%? So 0.002. Okay, and then I'm missing something. Oh, I should probably include 0, right? And so now, okay, I'm stuck. How do I know the probability for 0, right? I'm really stuck. I cry a little bit, and then I remember, okay, let's go back to the probability rules. Okay, all the probabilities are between 0 and 1. That's fine here. And then everything sums, or all the probabilities sum to 1. Oh, okay. So then I can add these all up. 0.51, 0.02 is 0.53 last I checked, and then subtracted from 1, 0.47. Again, what I did was a little bit of mental math. I did 1 minus 0.51 plus 0.02. So I used that complement rule, and then, or I just knew that everything had to add to 1. Okay? So there we go. There's my probability distribution. Boom, done. Moving on. write a probability statement for 0 people dated in the last 30 days and find its value. Oh, well, okay. So probability statement, P of 0 people dated, right? And what I'm going to do is show you a little bit of notation we'll see in the next video. We're going to call this x equals 0 because I defined this capital X as number of distinct people, okay? And so I'm saying probability that x is 0 in my table, and I found that to be 0.47 from above. Oh, okay, boom, done. That's our discrete probability model. Looking at continuous models, they're trickier, right? We can't put them in a nice neat table, but they're going to look like this. They're, line graphs of sorts. And so you can see 2 examples here. We'll work through information related to the first one. But when we talk about continuous probability models, we get what we call density curves. And that's really just this boundary curve here in each of the cases, okay? And each of these curves have 3 properties. Okay, they're always on or above the horizontal axis. That's 1. 2, area underneath. This is important. This is perhaps the most important one. Area is exactly 1. Total area. Okay. Third one, also super important. Not as important as the first or as the second one though. Okay. Probabilities are computed as area under the curve. Those of you who have taken calculus recognize that this is an integral. Okay, we're not going to compute integrals, and you don't need to know calculus, so breathe. Okay, probabilities are just area under the curve. Okay, and so one other thing to note with these before we go on and do an example is that these curves are often idealized. You might have seen like a histogram that's kind of wild before. Kind of like this one, and what you end up doing is fitting a curve over it that looks something like this. Okay, so you can use discrete data and extrapolate. Well, I don't want to say extrapolate, but you can create a density curve prediction for that data. Okay. All right. So nevertheless, here we go. Graph below shows average amount of time per day in our study. Okay, so context, 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 read, and here we go. Okay, so let x be the random variable representing the average amount of time. We want to interpret, okay, and find and state their values. Okay, so I'm going to do the first one, first 2. I'll do first 2. You do the second 2. Okay, so probability that x is equal to 2. Okay, I go to my graph. X is right. This is x. That's how it's been defined. And I'm saying x is 2. This is 0.25. Okay, and so I would just say that I'm too lazy to write this out, but this would be the probability that a random or that a student studies for average amount of time for an average of 2 days, 2 hours per day. Okay, that's what it is. And now this I'm going to say is actually wrong. Okay, this is wrong. This is a common answer. The actual answer is 0, right? What we're doing, remember, with a continuous probability function or probability model is computing area or computing probabilities as area. So what area does one point have? None, right? So don't fall into this trap of just, X and Y approach. You have to think about area. Okay, and a point has no area. Okay, in that regard, for number 2, probably that x is less than 2. So this would be in words, the probability that a student studies for 2 or fewer hours per day at UMR, and I would compute this by calculating the area that is that corresponds to 2 and under. Okay, so this triangular region, and luckily I remember how to compute the area of a triangle. Area of a triangle is 1/2 times the base, which is 2, and then times the height, which is 0.25. Okay, and this just comes out to be 0.25 after calculation. All right. All right, so using the notion that areas are computed as probabilities, calculate 3 and 4 for me. Resume the video when you're ready to see the answers. And here we go. Okay, so for 3, I just use the complement rule, right? Because this is less than 2, this is more than 2. They're complements of each other, so 0.75. For 4, I saw it as the green shade, well, it is the green shaded region, and I saw it as a rectangle, which is the second half over here. And then the first area here I saw as a trapezoid, and maybe you wanted to break it into a triangle or into a triangle and 2 rectangles. That's fine. I don't care. Using the trapezoid approach, area of a trapezoid is average of the bases times the height, and so that's what this is. And then the height is just 1. Okay, would be this way. And then for the rectangle, I did length times width. Okay, so I got my 4 answers. Okay, big thing, remember continuous density or continuous probability functions, they are um, or probabilities are measured as area. Okay, keep in mind that an area has to be 1, and then you should be good to go. And so points have no area. Okay.